In this video, we are going to be looking at current division rule and voltage drop. As we said in our previous videos, when current gets to a junction or a node, it splits. How is this splitting done? That is what we are going to look at. Let's look at this circuit on our screen. In this circuit, we can see that we have a voltage source which is directly across a resistor R1, and then the R1 is also in parallel with resistor R2, because you can go through both resistors and come back to your starting points without meeting any other elements. And so resistors R1 and R2 are in parallel. What that means is that when the total current leaves the voltage source and gets to this node, it splits into I1, which is the current through resistor 1, and then R2, which is the current through resistor 2. To find these currents, we need to determine the voltage across the resistors, and then we divide the voltages by the resistors, or the values of the resistors, to get the currents. So for example, for I1 is the current through R1, and so if we know what the voltage across R1 is, then we can do V over R1 to get I1. Same logic applies to I2. If we know the voltage V across R2, then we can do V over R2 to get I2. Now, since the voltage V, the total voltage of the circuit, is directly across R1, the voltage across R1 is also V. And since R1 and R2 are in parallel, the voltage across R2 will also be V. To find the value of V is the total voltage of the circuit, and so it is the total current, or the current leaving the source, times the total resistance. The total resistance of the circuit, since there are only two resistors, R1 and R2, and they are in parallel, R1 and R2 are in parallel, is equal to R1 R2 over R1 plus R2. What that means is that the total voltage of the circuit V is I R1 R2 over R1 plus R2. Now, to find I1, as we've already explained, I1 is simply V over R1. V is I R1 R2 over R1 plus R2 from here, and so this divided by R1 is what gives I1. This resolves to be times 1 over R1. R1 cancels R1, and so you have I R2 over R1 plus R2 times, over R1 plus R2. So this is I1. Now let's apply the same logic for I2. I2 is simply V over R2, which is equal to the V, which is I R1 R2 over R1 plus R2, divided by R2. Right, this becomes times 1 over R2, and then R2 cancels R2 to give you I R1 over R1 plus R2. What that means is that our I1 from here is simply equal to R2 over R1 plus R2 times I, and then our I2 from here is equal to R1 over R1 plus R2 times I. Now, looking at this carefully, we can see that the value for current I1 is simply the other resistor that it shares the current with, which is R2, over the sum of their resistor values times the currents they are sharing. Same applies to I2. I2 is simply the other resistor that it is sharing the current with, which is R1, over the sum of the values of their resistors times the currents they are sharing. And so to find the currents through a particular resistor, once it is sharing a current with another resistor, it is simply the other resistor over the sum of the values of their resistances times the currents they are sharing. Now, it is important to note that this rule apply even if the direction of one of the currents opposes the natural flow of currents. Considering this circuit, what I'm referring to is that the total current leaves the voltage source. It gets here, naturally it's supposed to split downwards and then towards the right. And so from what we just studied, the one that goes downward, I1, is simply the other resistor, which is R2, over the sum R1 plus R2 times the current they are sharing, I. The current that was supposed to move towards the right, which is I2, is also simply R1, the other resistor R1, over the sum R1 plus R2 times the current they are sharing, I. However, since I in this circuit has been shown to be moving opposite the natural flow of the current I2, what we do is that we negate I2, and so I2 in this circuit is negative R1 over R1 plus R2 times I. Let's look at this example. To find I1 is the current passing through the 3 ohm and the 2 ohm. 3 ohm and the 2 ohm are in parallel, and they are sharing the current 10 amps. And so to find I1, it is simply the other resistor, which is the 2 ohm, over the sum 3 plus 2 times the current they are sharing, 10. This results to be 4 amps. I2, which naturally should be moving towards this direction, but because the direction of the current I2 is shown to move opposite the natural direction, is simply negative of the other resistor, which is 3 over the sum 3 plus 2 times 10. This results to be negative 6 amps. And so that is basically the current division rule. Let's look at this example as well. So for this example, we are supposed to determine the current I1. The current I1 is the portion of this 10 amp that splits into the 3 ohms. Note, however, that the current that is going to be shared, or the division of the 10 ohms, is going to be at this junction between these 3 ohms and then the combination of the rest of the parallel circuits here. And so before we can apply current division rule, we have to resolve these two resistors in parallel to make it one resistor, so that we can apply our current division rule. What that means is that 2 and 2 in parallel is simply 2 times 2 over 2 plus 2, which results to be 1 ohm. And so our new circuit looks like this. And then a combination of the 2 and 2, which is 1 ohm. So this is I1 that we are supposed to find, and then this is 10 amps, and this is V. Okay, so now to find the value of I1, we apply current division rule. So I1 is simply the other resistor, which is 1 in this case, 1 over the sum 3 plus 1 times the current they are sharing, 10. And so this results to be 10 over 4 amps. Right. Let's look at voltage drop next. Anytime current passes through a resistor, what happens is that voltage is dropped in that resistor. The voltage dropped in that resistor is simply the product of the resistance and the currents passing through that resistor. And so for this circuit, when I passes through R1, a voltage V1 is dropped, and then the voltage V1 is simply a product of the currents that is passing through R1 times R1. Same applies for R2. When the current passes through R2, voltage V2 is dropped, and then the voltage V2 is simply the product of I, which is the current passing through R2, times the resistance R2. For resistors in series, as we explained in our previous video, we said that resistors in series share the voltage. What that means is that the voltage V, which is across these two resistors in series, divides amongst the resistors. What that means is that the total voltage V is equal to the voltage that drops in V1 in R1, which is V1, plus the voltage that drops in V2 in R2, which is V2. Let's look at this example. In this circuit, we are to find the values of I and R in the circuits. And so I is the currents passing through both resistors, R and then 3 ohms, and then R is the resistance of the first resistor. What we've been given in the circuits is, we know what the total voltage is, V, which is 10 volts, and then we know the voltage that is dropped in the first resistor, V1, which is 4 volts. We also know the resistance of the second resistor, R2, which is 3 ohms. And so we have to find R and then I. Based on what we just explained, we have two resistors, R and then 3 ohms in series. So what is going to happen is that they are going to share the voltage 10 volts across them. We already know from this circuit the amount of voltage that has dropped in the first resistor, and so to find the voltage across the second resistor, V2, it is simply the total voltage V minus what has dropped in the first resistor, V1. So this is equal to 10, which is the total voltage, minus what has dropped in V1, 4, and so this results to be 6 volts. And so we have 6 volts here. Now, since these two resistors are in series, what that means is that the same currents passes through them. To find the currents that is passing through the second resistor, 3 ohms, all we need to do is to divide the voltage across that resistor by the resistance. And so what that means is that I, which is the current passing through the 3 ohms, is equal to the voltage 6 over the resistance 3, and this results to be 2 amps. What that means is that our I is equal to 2 amps. Now, to find R, what we can do is to divide the voltage across the resistor R. To find R, we can divide the voltage across the resistor R, which is V1 or 4 volts, by the currents I, which we just found to be 2 amps. And so resistor R is simply 4 divided by 2, which results to be 2 ohms. Now let's look at this circuit. We are to find the value of I in this circuit. The value of I has been denoted as this in the circuit. To find this, we can quickly see that we need to find what the total current of the circuit is, the current that leaves the voltage source, so that we can use current division to determine where the current goes and what's not. We know the total voltage of the circuit because there's only one source in the circuit, and it is 25 volts. To find the total current I, we need to find the total resistance RT. We need to find the total resistance, or the effective resistance. So we go back to our previous video where we discussed effective resistance. To find the effective resistance, the first step is to check current flow and to see the resistors in which currents will flow. And so once we trace the current from this source, what happens is that when it gets here, it splits between this and this. When the one that splits here gets here, splits between this and this. And then when the one that splits through the 3 ohms gets here, because there's a short circuit here, all of the currents will pass through this and then go back to the source. What that means is that, and then the one that branches towards the left also passes through the 4 ohms and comes back to the source. What that means is that the 3.5 ohms, 5 ohms and 7 ohms do not contribute to the effective resistance of the circuit. And so we can redraw the circuits to look like this. So you have your 1 ohm here, 25 volts, 2 ohms here, your 3 ohms here, and then the remaining parts are cut away from the circuits. So you have, this is 4 ohms, 25 volts, this is 1 ohm, this is 2 ohms, and then this is 3 ohms. Now we can find the total resistance or effective resistance of the circuit. To find the effective resistance of the circuit, we identify resistors in parallel and in series. We can clearly see from this circuit that 2 will be in parallel with 3, and so 2 is in parallel with 3. 2 parallel with 3 gives us 2 times 3 over 2 plus 3, which results to be 6 or 5. And so what that means is that this part of the circuit becomes 6 over 5 ohms. From this our new circuit, we can also clearly see that the 4 ohm and the 6 over 5 ohm are also in parallel, because we can go through both resistors without meeting any other elements, and so they are in parallel. So what that results to is we have 4 in parallel with 6 on 5, which is 4 times 6 on 5 over 4 plus 6 on 5, and this results to be and this resolves to be 12 over 13. And so if we draw the circuits up here, this is how it will look like. So you have a resistor 12 over 13, and then you have your 1 ohm, and then you have your voltage source. So you have 12 over 13 ohms, you have your 1 ohm, and then you have your voltage source. Now from this circuit, we can clearly tell that the total resistance of this circuit is simply the 12 over 13 ohms in series with the 1 ohm, because there's no node or junction between them. And so the total resistance is 12 over 13 plus 1. And so the total resistance of the circuit is 25 over 13. Now that we know what the total resistance of the circuit is, we can find what the total current is. And so the total current here is simply the voltage, total voltage 25 divided by the total current, which is 25 over 13. If you evaluate this, you get 13 amps to be the total current. What that means is that for the circuit, from the voltage source, 13 amps is what leaves the voltage source, 13 amps. Okay, now when this 13 amps gets to the node, what will happen is that it will split between this and then the right part of the circuits that contributes to the effective resistance. So it will split between the 4 ohm and then the combination of these 2 and 3. These ones don't come in because they don't receive any currents, and so they are out of the circuit. And so this current 13 amps will split between the 4 ohms and then the combination of these 2 and 3 in parallel. Now resolving 2 and 3 in parallel is what gives us this circuit, and so it gives us 6 over 5 in parallel with 4. And so we can use this circuit to determine how the current will divide at that junction. So this is our 13 amps. When it gets to this junction, it's supposed to split between 4 and then the 6.5 ohms. The one that splits to the 4 ohms is supposed to naturally move toward the left. But then if you look at our circuits in the question, the I that we've been asked to find is moving opposite the natural direction of that current. So what that means is that our I that we're supposed to find is negative of the currents that will flow through the 4 ohms. So we apply current divider rule here. To apply current divider rule, we do the other resistor, which is 6 over 5, divided by the sum, which is 4 plus 6 on 5, times the currents they are sharing, which is the 13 amps, times 13. And so once you resolve this, you get I to be equal to negative 3 amps. And so the current I that will be asked to find is equal to negative 3 amps.